Okay, good evening, everybody, and welcome to the first online review session in organic chemistry for the fall 2013 semester. In today's session, we are going to review for the first exam, exam number 1, that is scheduled for Thursday, September 26th. And for this review session, we are going to use materials from a previous exam number 1 that was given in the fall of 2012. Okay, before we get the session started, let me go ahead and acknowledge those of you who have joined us tonight. I see Amit. I see Von Lea Rickerson, Bethlehem Agize, Brittany Galloway, Shante Smith, Christian Bradley, Danuchika Gelin, Erin Walkers, Ganesh Mohan, Joanna Gastin, Kiara Wallace, Makiva Walker, Mashake Hutchinson, Nolan English, Robin Onoha, Rone Raymond, Sachin Pasikaran, Sipora Christopher. And finally, we have Victoria Faulkner. Okay, you are all welcome. Okay, so to get the session started, what I'm going to do here is to ask one of you to read the first question. Oh, by the way, before we go to the first question, do you guys have any preference as to which question you want us to go over tonight? If you have any preference, you could send me the preference through the chat window right here. Okay, I see 9. Somebody said 9. Okay, 15, 16, 17. Okay, very good. And we go over the final page. Okay, good. Okay. Okay, great. Okay. Okay, so let us see here. I see most people do want us to go over some of the more difficult ones. So let us start with this here. Number 5. Okay. Okay, Erin Walters, can you go ahead and read this question for us?
Which question? Oh, 5. Draw
Yes.
orbital picture of a molecule containing 2 sp2 hybridized carbon atoms and 4 hydrogen atoms, showing all the valence electrons.
Okay, very good, and thank you. Okay, so what this question is asking you to do here is draw the orbital picture of a molecule that has 2 sp2 hybridized carbon atoms and 4 hydrogen atoms. So in essence, what this question is asking you to do is to draw the orbital picture of this molecule here. Okay, this molecule we call ethylene. If you look at this molecule here, you have sigma bond and another sigma bond here. You also have sigma bond here. And another sigma bond here. And in this double bond here, this carbon-carbon double bond, you also have 1 sigma bond. And of course here you have a pi bond right here. This is a pi bond. In essence, this carbon here and this carbon here, these are sp2 hybridized carbon. They already told you that. Okay? So when you have an sp2 hybridized carbon, what that tells you, if you want to draw the orbital picture, say we have this carbon here, what that tells you is that you must have 3 sp2 hybridized orbitals. So therefore, let us draw those hybridized orbitals. So you have this. Those sp2 hybridized orbitals, which are about 120 degrees angle to each other. Okay, so that is one carbon here, which is sp2 hybridized. Then you have another carbon here. Okay, let me do that better than that. And do this. Okay, so these are the sp2 hybridized orbitals. Then you have the other carbon atom here, also as an sp2 hybridized orbital. Okay. Now, in addition to those sp2 hybridized orbitals, since it is sp2 hybridized, you then have p orbitals left on each one of the carbon atom. So p orbital, p orbital, p orbital, and p orbital. And on this sp2 hybridized orbital, you have 1 electron each. So you have electron, electron, okay, electron here, electron here, electron here, electron here. Okay? And then you also have the, in this case, the the s orbital from hydrogen overlapping with the sp2 hybridized orbital with another electron overlapping here, hydrogen with another electron overlapping here, another electron overlapping here, another electron. So now what do we have now? We have made the face-to-face or head-to-head overlap, giving the sigma bonds, the head-to-head overlap. Which gives you the sigma bonds. Okay. Now, since we now know, right now we have carbon is having only 3 bonds each one of these carbon atoms. But we do know that carbon is tetravalent. So therefore, this p orbital that has electron and this p orbital that also has electron, they will overlap. Imagine that they overlap. And when they overlap, they therefore form what we call the pi bond. This is your pi bond. And here, this will be your sigma bond. And this is another sigma bond. This is another sigma bond. And this is another sigma bond. So what you have here, of course, this is a sigma bond also. So what I've given you here, this is the orbital picture of this molecule that we call ethylene. So whenever you are told to give the orbital picture, in essence, you have to give all of the bonding, show all of the bonding orbitals. In this case, we have an sp2 carbon giving us sp2 hybridized orbitals, and then you have the s orbital from hydrogen overlapping with those sp2 hybridized orbitals to form your sigma bond, and then the remaining p orbitals on each of the carbon atoms is used to form your pi bond. Okay, is there any question on this before we go to the next one? If that is clear to you, give me a happy face. If it is clear, give me a happy face. Okay. Okay, good. Okay, good. Okay, very good. Okay, so let us go to question number 6. Okay, Kiara, can you go ahead and read question number 6 for us?
Which of the following species is a Lewis acid?
Okay, thank you. I'm very good. Okay, so this question is asking which of the following species is a Lewis acid. Of course, we know a Lewis acid equals to an electron acceptor. Now, any species that accept electron will be considered a Lewis acid. So what would be the answer to that? Number 4, or D. Very good. Okay, so the answer is this. Everybody say, okay, why is D correct, by the way? Why is this correct? That is correct, but why is it correct? Let us draw the, okay, this is boron tribromide. Let us draw the structure. You have boron here. You have bromine. You have bromine. You have bromine. So why is this correct? Yes, somebody wants to ask me a question. Who is that person? Go ahead and ask your question.
Well, it's not
either pick up the mic or send me your, yeah.
It's not.
Go ahead.
I was just saying because B and C give off hydrogen, that's why those two aren't correct.
Okay, okay. About boron, why is that is you are on the right path. Why is this one correct? D. Okay, if you take a look at this molecule here, boron tribromide. Does this molecule have an octet of electrons surrounding the boron? You notice we told you that to have a stable molecule, at least for those atoms in the in group 2 of the periodic table, they need to have an octet of electrons in their valence shell of any given compound. Does this boron, does it have an octet of electrons? Yes or no? Say yes, just why or no? Does it? No. Okay. So it has only 6 electrons. That means this molecule here will be eager to accept electrons. Essentially, what that tells you is that this molecule must have a vacant p orbital. It must have a vacant p orbital that is ready to accept electron. And that vacant p orbital can very easily accept electron, thereby this molecule becomes a Lewis acid. Okay? Okay, let us go to the next one. Okay, Robin Onoha, can you read number 7 for us?
Which of the following molecules has a net molecular dipole?
Okay, very good, and thank you. Okay, so this question asks you, which of the following molecules has a net molecular dipole? Okay, so which will be the correct answer here? Which will be the correct answer? Let us see. B, somebody said B. Yes, yes. Okay, B is correct. Yes, that is correct. B is correct. Okay, why is B correct? Let us draw the structure of B to see why that would be correct. So we have B is methanol or methyl alcohol. Okay, so where would be the direction of the dipole here? Let me say this is left and say this is right. Just say left or right. Where would be the direction of the dipole here? Is it toward the right or toward the right? Exactly. And that is because oxygen is a lot more electronegative than carbon atom. So therefore the direction of this dipole here with relation to this bond right here, direction will be towards oxygen. Okay, so we expect to have a partial positive charge on carbon and a partial negative charge on oxygen. Now you also see here, because of the non-bonding pair of electrons, so the overall direction of the dipole for this molecule will be towards right here. The overall direction of dipole for this molecule will be in this direction right here. So the answer to this is that this molecule will have a net molecular dipole because of the greater electronegativity of the oxygen relative to carbon atom. Also, you notice here, in terms of the oxygen and hydrogen, the direction of the dipole will also be towards the oxygen. Okay? Okay, so let us continue. Okay. Raymond, can you go ahead and read question 8 for us?
Which of the following statements is true of our resonance structure?
Okay, thank you, and very good. Okay, so this question says, which of the following statements is true about resonance structures? Okay, so what would be the answer here? Which is the answer here? Let's see. C. Everybody got that right. Very good. Everybody says C. What is C? They contain the same arrangement of atoms. Excellent. That is correct. In other words, whenever you are writing resonance, say for example, if you have this molecule here, if I tell you to write the resonance structure for this molecule, keep in mind in resonance, all you want to do is simply move either pi electrons or non-bonding electrons. You do not move the atoms. And that is why we say they contain the same arrangement of atoms. So for this, if I want to write resonance for this molecule, I could think of a movement of electron in which I move this pi electron here, I move to oxygen, and if I do that, I get this. Now I will have a formal charge on oxygen of -1 and a formal charge on this carbon here of +1 because I moved the electron away from this carbon. And so therefore, molecule A and molecule B will be considered resonance structures. And you see what we have done here, we did not move the skeleton of the atom skeleton. In other words, the attachment of the atoms is still the same. Okay, we did not move them. Okay, all we have done here is to move the pi electron to oxygen. Okay, let us go to the next one. Okay, this is a good one for resonance. Okay, Danuchika Gelin, can you go ahead and read question 9 for us?
For the molecule below, write 3 additional resonance structures that do not have positive charges.
Okay, thank you, and very good. Okay, so what they have here, say for the molecule below, which is this molecule here, write 3 additional resonance structures that do not have positive charge or charges. Okay, so what do we need to do here? Okay, so we already know that this molecule that we have here is negatively charged. So in essence, this question is telling you, whatever resonance structure you draw here, you cannot have positive charge, but you could, of course, have negative charge. Okay, let us see. We told you that all you do with resonance is to move pi electron. Supposing, therefore, if I move this, keep in mind, these two non-bonding pair of electrons on this carbon here, what that tells you is that you have a p orbital that contains those two electrons. And also, if you look at this carbon here, this carbon, of course, you know you have hydrogen here. We just don't show it. We also have hydrogen here, which is not shown. But the point here is this carbon and this carbon are sp2 hybridized carbon, which means that they also have p orbitals that you could move electron into. The same thing on this carbon here, sp2 hybridized carbon, sp2 hybridized carbon. So you have those p orbitals on those carbon also. So let us see what we can do here. Supposing we move these two non-bonding electrons, we move it to form a bond between this carbon and this carbon. So I move those two here to form a bond between here and here. And when you do that, you have to move the electron away from this p orbital. And then I move it into the p orbital on this carbon. So you have to be very precise in what you do here. And so doing, therefore, I have this. I have the carbon-oxygen double bond. I did not change anything here, so that should stay there. Now, since I moved this pi electron to this carbon, I have those two electrons here now. That means that carbon will be negatively charged. And also, since I moved these two non-bonding electrons to form a bond between this carbon and this carbon, now I have a double bond right here. Okay? So, this is an acceptable resonance structure. You notice this resonance structure does not have a positive charge on it. Okay, then I could also take a look at this molecule again. Let me take this out so I don't confuse you. I could do the same thing that I did on this side of the molecule. Since this is an sp2 carbon, I could move this here to form a pi bond, and then in so doing, I move the two electrons here that was between these two p orbitals. I move them to this p orbital here. Are we missing a pair or no? Oh, yes. Thank you. Thank you. We are missing a pair right here. Thank you very much. Okay. So we now have this here. So let us now draw the resonance structure. Oh, by the way, folks, anytime you see me making an error, please make sure you point this out to me before we go too far into our discussion. Okay, so now we have, this will be still here. Okay, now this will be here now. This is now here, double with a electron on this carbon, so now that carbon is negatively charged. And since we did not do anything on this carbon, this is also here. Okay, so now we have two additional resonance structures. Now we could now draw another resonance structure involving the carbon-oxygen double bond. Supposing I now do this. By the way, let me take this out so that it doesn't confuse anybody. Okay, supposing I now do this, I move this here, these two non-bonding electrons on this carbon, I move to here to form a bond between this carbon and this carbon. And when you do that, you have to move this pi electron away from this carbon, because carbon cannot have more than 4 bonds. Okay, so we move the pi electron away and we'll place it on the p orbital of oxygen. Somebody asked a question. The line underneath the non-bonding electron is negative. The non-bonding electron is, yes, this is, yes, right here. This is negative, right? Okay. So now we have this. Sometimes, folks, whenever you ask me a question, in order to get my attention, you may want to click on this electronic hand raising here. That way I will get a chance to either read your question, or sometimes you may want to pick up the mic and simply ask your question. Okay, so if we do that, now we have this. That is now negatively charged. Now the double bond is here. Now we are going to have this here. Now we are going to have this here. Okay, so now this here, A, B, and C, these are all resonance structures of this compound here. Let us call this compound, what do we want to call this? D, of compound D. Okay, so A, B, C are resonance structures of the same molecule right here. Okay, is there any question on this before we move on? And notice what we have done here. In resonance, all you are doing is to move the pi electron or the non-bonding pair of electrons. That is all you are doing. Okay, if there is no question, let us go to the next one. By the way, for those of you who may not still understand some of this thing about resonance, I will be in my office tomorrow from about 12 p.m. So if you want to stop by, you are welcome. Okay, let us see here. I think we did it in class already, so we don't need to go through this. Go to this. Okay, 11. Brittany Galloway, can you read number 11 for us?
Using the names below, draw the semi-condensed structures and write the correct IUPAC name for each molecule.
Okay, thank you, and very good. Okay, so what do they have here? They're using the names below, which are these names here. Draw the semi-condensed structures and write the correct IUPAC name for each molecule. Okay. Presumably, the names that have been given here are wrong, so therefore we need to draw the structure from these names and then give the correct names. So let us start with, let me ask you this. I need some help here. Let us start with A. What would be the, according to the name that we have here, what is the parent name for this molecule? How many carbons in the parent name? Just give me the number of carbons. 6, exactly. It is hexane, so it is 6 carbon. So let us go ahead and do that. So the parent name contains 6 carbon. It's a semi-condensed structure, okay? Okay. Let me say here, according to this, this is 1, 2, 3, 4, 5, and 6. Okay, so it now says 2-ethyl. Okay. So let me take 1 hydrogen out. Now, first, notice what I do here when anytime I want to put a substituent. Notice that I remove one of the hydrogen. The reason I keep doing that, because many of you simply place a substituent, say for example on this carbon here, without removing the hydrogen. If you do that, you will be losing point, because keep in mind, carbon is tetravalent. You cannot give carbon more than 4 bonds. Okay, so therefore this here has an ethyl group, and then it says 4-methyl. So if this is carbon 1, 2, 3, and 4, the methyl will be here. So I remove that hydrogen, and I place a methyl right here. Now we want to name this molecule. Can anybody tell me what would be the carbon in the base name of this molecule? The number of carbons in the base name for this molecule. Let us call it molecule A. 7, exactly. 7. Very good. Excellent. So 7. So now the question is, where do we start counting? Let us say that we start counting from here. Do we start counting from here? Let us see. 1, 2, 3, 4, 5, 6, and 7. Let us say we start counting from there, because keep in mind, you want to give your substituent the lowest combination of numbers. So this methyl here is a substituent, and this other methyl here is another substituent. Okay? So you have substituent in position 3 and 5. Okay, so what would be the name for this molecule? Can anybody give us the name? What would be the name for this molecule? Can you write the name for me? Just send through the text. Okay, message 3,5-dimethyl heptane. Excellent. Let us see. 3, 5. Very good. 3, 5-dimethyl heptane. Okay, that is correct. Okay, I think everybody got that right. Okay, now let us go to B. Okay, just taking a look at B right now. What do you think might be wrong with B? Just taking a look at what they have there. Can anybody tell me? Either pick up the mic or just send through the text message. Alphabetical order is wrong. Very good. Excellent. I'm glad you guys got that. The alphabetical order is wrong. Ethyl should come before methyl, as to start with. And also, when you do not need an hyphen between the substituent name and the parent name. You do not need an hyphen here. Okay, so those two things are wrong. Okay, now let us take a look at this, and based on what we have there, and draw the appropriate molecule. Say hexane is the base name or parent name. Okay, so that is hexane, and it says 2-methyl. So I remove one hydrogen here. I place a methyl here. And then say 4-ethyl. That's 1, 2, 3, and 4. So I remove one hydrogen here. I place an ethyl group. Okay, so therefore, what will be the name for this? Can anybody give us the name? Oh, by the way, let me number this. Let us see the numbering here. It doesn't really matter. Can we go here or here? or here to here, which we want to go. We want to give the lowest combination of numbers. So we want to say 1, 2, 3, 4, 5, and 6. Okay. So what would be the name for this molecule? 4-ethyl-2-methyl-hexane. Excellent, excellent. Okay. Yes, very good. 4-ethyl, 4-ethyl, 2-methyl-hexane. Keep in mind, when you write the parent name or the base name and the substituent name, there is no space between them. No space between them, okay? Okay, if there is no question on this, let us move on. Okay, it's getting more interesting now. Let's see. Marcia K. Hutchinson, can you read number 12 for us?
Write the skeletal structures and IUPAC names for 5 constitutional isomers of methyl cyclohexane. Each of the isomers must contain only 1 sigma bond.
Okay, thank you, and very good. Okay, so what this question says is, write the skeletal structures and IUPAC names for 5 constitutional isomers of methyl cyclohexane, this molecule here. Each of the isomers must contain only sigma bonds. In other words, what they are telling you here, all of the carbon atoms in this molecule must be sp3 hybridized carbon atom. Okay, so the molecule they have given us is this here. Cyclohexane. Okay, that is methyl cyclohexane. That is the molecule they have given us, and that molecule contains 7 carbon atoms. So let us go ahead and write the molecular formula, which is C7H14. Is that right? That is 3 hydrogen, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is the formula they are asking us to use. In other words, draw constitutional isomers from this. You could draw as many constitutional isomers as you want, but in this case, I do not want to waste your time, so I ask you to give me only 5. Okay, so let us try. Supposing we have, let's start with this here. Okay, and you are supposed to give the name also. So supposing we have this, constitutional isomers. That would be 1. And what is the name of this? 1,2-dimethyl cyclopentane. Okay. We could also have this. Keep in mind, whenever you are drawing constitutional isomers, these are compounds with the same molecular formula, but with different attachment of the atoms. Okay, in this case, we could place this here, a methyl here, and another methyl here. So that would be another constitutional isomer of this molecule. So in this case, the name would be dimethyl cyclopentane. I will go ahead and do 4. I will leave the rest to you, but you could draw as many as, God knows, as many as possible here. Okay, I could also have this. Supposing I have a methyl here, and another methyl here. Okay? In that case, this becomes 1,1-dimethyl cyclopentane. Okay? Okay, now I will also have this. Instead of 5-carbon ring, I could have a, let me do that better. I could have a 4-carbon ring, cyclobutane ring. I could have this. Okay, if I do that, I need 3 more carbons, so I could have this here, this here, this here. This will also be a constitutional isomer of this molecule. As long as you are using the same molecular formula, the only difference will be the attachment of the atoms. So this becomes 1, 2, 3 trimethyl cyclobutane. Oh, by the way, they do ask us to do the skeleton. Okay, let me do the skeleton for this. For this here, the skeleton will be this. Just this and this. That will be the skeleton for that. For this, that will be, for here, this will be this here. That will be the skeleton for that. For this, that will be the skeleton for that. For this, that will be the skeleton for that. Okay. Now, let me create some. Okay, let me just take this out here. Let me draw one more. Okay. Just to show you what you can really do with this. Okay, I could also have a 3-member ring. I could have a 3-member ring, so that is 3 carbon. I need 4 more carbon. In which case now I have, if you want the skeletal structure, that's an AT group. That's another AT group. So in this case, this will become, let me take this out so I could write the name. So the name for this will become 1,2-diethyl cyclopropane. So you could write as many as you want, but some of you may come out with different ones than the one I have here. But the point to be made is, whenever you are doing constitutional isomers, these are molecules with the same molecular formula. The only difference between them is the attachment of the atoms are different. Okay? Okay, is there any question on this before we move on? Okay. Okay, so let us go to the next one. Okay. Nolan, English, can you read number 13 for us?
Sure. 13. Write structures and names that fit the following features. 16 points. A cycloalkane that has only secondary carbon. B, an alkane with only primary and quaternary carbon. C, an alkane that only has 6 primary carbons and 2 quaternary carbons. And D, a tertiary alcohol.
Okay, thank you very much. Very good. Okay, so this question here is asking you to do a lot. It says write structures and names that fit the following features. Okay, let us do 13. Let us do A together. A cycloalkane that has only secondary carbons. Okay, can anybody give me an example that will fit this? Cycloalkane that has only secondary carbon. Anybody has an idea? Pick up the mic or send it to me through the chat window. Okay, cyclobutane, excellent. Yes, cyclobutane will be an example. That is correct. Okay, if you look at cyclobutane, this carbon here, this is a secondary carbon because it is attached to 2 other carbon atoms. This carbon here, it is a secondary carbon because it is attached to 2 other carbon atoms. The same thing goes to this carbon, and the same thing goes to this carbon. Okay, very good. Okay, we could also use cyclohexane or cyclopropane. Any one of those will do. Okay, about B, an alkane with only primary and quaternary carbons. Does anybody know an example of that? An alkane with only primary and quaternary carbons. Okay, primary and quaternary carbon. Keep in mind, a primary carbon is only attached to, let me see here. A primary carbon is only attached to 1 other carbon. Okay, 2,2-dimethylpropane. Excellent, excellent. You guys, I think you guys got that right. 2,2-dimethylpropane. Okay, which will be this here. Is that what you, oh, you say 2,2-dimethylpropane. Okay, let me take that out. Very good. That is correct. This here, each one of the methyl group is a primary carbon. This, and this, these are primary carbons. And of course, this is your quaternary carbon right here. A quaternary carbon is attached to 4 other carbon atoms. Okay, how about C? An alkane that only has 6 primary carbons and 2 quaternary carbons. I think we can do that very easily. Okay, that will be for C, because you have here, you have 6 primary carbons here and 2 quaternary carbons. And finally, on question number 13, it says a tertiary alcohol. Okay, now, a tertiary alcohol means that you have an hydroxy group attached to a tertiary carbon. That is what that tells you. Whenever we say tertiary whatever, if we say tertiary amine, tertiary alcohol, tertiary chloride, what that tells you is that the functional group of interest is attached to a tertiary carbon, or I could say a primary carbon, or a secondary carbon. In this case, it could be this here. Okay, we will call this a tertiary. This we call a tertiary alcohol because the hydroxy group is attached to this tertiary carbon right here. I could also have this. This is also a tertiary alcohol because this alcohol, this hydroxy group, is attached to this carbon here, which is a tertiary carbon. Supposing I ask you to give me a primary alcohol, so in that case, you have to give me a molecule in which the hydroxy group is attached to a primary carbon. For example, ethyl alcohol. This is a primary alcohol right here because this hydroxy group is attached to a primary carbon. Okay? Okay, I think that should be clear to everybody. Let us go to the next one. We are moving right along. We have 10 more minutes to go. Okay. Okay. Avonia Rickerson, can you go ahead and read question 14 for us?
How many chlorocycloalkane constitutional isomers does the formula C4H7Cl have?
Okay, very good, and thank you. Okay, does anybody have an answer to this? What would be the answer to this question? Okay, let's see. Anybody giving that a try? Okay, what could be the answer to this? Okay, any try? You pick up the mic or you send me. Okay, C. Yes, C is correct. C is correct. That is correct. Why is C correct? Let us look at it. How many chlorocycloalkane constitutional isomers does this formula have? So they have given us the formula. It only has 4 carbon atoms. So okay, so let us go ahead and draw the possible isomers. Okay, this would be chlorocyclobutane. We could also have this. Okay, this will be 1-chloro, 2-methyl cyclopropane, 1-chloro, 2-methyl cyclopropane. Okay, we could also have this. And this will be 1-chloro, 1-methyl cyclopropane. And finally, we could have this. Notice how we do this, just changing the attachment. And this will be called, this will be a complex substituent right here. We put that in paren, chloro, methyl, chloromethyl, cyclopropane, because this chloromethyl group right here is attached to cyclopropane. Okay, so those are the 4 possibilities. Is there any question on this? Okay, let us go to the next one. Constitutional isomers, by now everybody should be able to do constitutional isomers. Okay. Okay, Amit, can you go ahead and read question 15 for us?
How many chlorocycloalkane isomers does the formula C4H7Cl have?
Okay, thank you. In this case, we are making this a little bit more difficult. Now you have to show the constitutional isomers and the cis-trans isomers. Okay, if you recall, this is the same question that we did in the last section. Okay, the answer to this, I will help you out here, will be this one here, 5. If you recall, in that last section, we have this. Okay, just stay online. If you can hear me, give me a happy face. Okay, good. See, what happened there, we lost internet service for a brief second there, so we are back online. Very good. Okay, so we have, in the last section, we have this, right? Okay, we also add this one here. And finally, we add this. Okay, so in the last question, we say we had a total of 4. But now, we are going to have a total of 5 because in this question, they are also asking us to do both constitutional isomers and cis-trans isomers. Now, if you take a look at this here, this molecule here, we could draw cis-trans isomers of this molecule here. So in other words, we get 2 isomers from this, 2 stereoisomers from this, cis-trans isomers, in which case you have this methyl could be going away from you, and the chlorine could be coming at you. In this case, this becomes a trans isomer. This becomes trans 1-chloro, 1-methyl, cyclopropane. And then we could then draw the cis isomers in which the 2 substituents will be on the same side of the ring. On the same side of the ring, which you have this, you say both of them are going away or both of them are coming at you. They will be the same thing. So now we have the now this is the cis isomer. This will be the cis isomer. A cis-trans isomer to this molecule here. So now what do we have? Keep in mind that these 2 came from here, so we could take this out. So what is the total number that we have now? We have 1, 2, 3, 4, and 5. Okay, is that clear to you? Can't CH3 be coming at you? Yes, both the CH3, CH3 and chlorine could be coming at you. They will still be the same compound. Okay, if this methyl and this here are coming at you, it will be the same molecule. Okay, we will still call it cis. In this case, we will still be cis. 1 chloro, 1 methyl, cyclopropane. Okay? Okay, so let us go to the next one. Okay. Okay, if I have not called on you tonight to read a question for us and your mic is working, can you go ahead and read this for us? Question number 16. Okay, if nobody is doing that, let me see. Go back to the beginning. Erin Walters, can you go ahead and read question 16 for us?
An halogenation reaction of compound A with molecular formula C6H12 only gave one monochloral product. Write the structure of compound A and the product.
Okay, thank you, and very, very good. Okay, so in this case, we are now getting to reactions of alkanes and cycloalkanes. Now you say an halogenation reaction of compound A with a molecular formula C6H12 only gave one monochloro product. Write the structure of compound A and the product. Now, if you take a look at this, the formula that we have here is C6H12. Remember, the general formula for alkane is CnH2n plus 2. And the general formula for cycloalkane is CnH2n. This is cycloalkane, and this is for alkanes. And this here is for cycloalkanes. Okay, so what does this formula therefore tell you? This C6H12, will this be a cycloalkane or an alkane? Just give me your answer. Will it be, this here be a cycloalkane or an alkane? A cyclo, excellent, because of the formula. Very good. So if it is going to be a cycloalkane, let me also give you a little bit of background information here. If we have this, now let me go back a little. Supposing I have this. And I do halogenation. Halogenation simply means we are reacting a molecule with an halogen, for example, chlorine or bromine, in the presence of light. In this case, let us say chlorination. And in the process, we are going to replace the hydrogen with chlorine. So we call this halogenation. This is the organic product here, and the inorganic product is right here. Now, if you take a look at this, we have in this molecule here that we call methane, we have 4 different types of hydrogen. Okay? All of these hydrogens here, these are what we call chemically equivalent hydrogen. Chemically equivalent hydrogens. In other words, if I replace any one of these with chlorine, I get the same product. This will be chloro. If I replace with only one chlorine atom, I get one product. It doesn't matter which one of them I replace, because all of these here are chemically equivalent hydrogen. Okay? Now let us go make it a little bit more complex. Supposing I have this. Supposing I also now have this. Just follow me now. I do, let us use bromination, it doesn't matter, we could say bromination. Okay? In the presence of light, what do I get? If I replace one of the hydrogen with bromine, you say, what happened to the other carbon? Well, anyway, if I replace this hydrogen with bromine, I get this product. In other words, no matter which hydrogen I replace here, I will get only one monochloro product, which will be, in this case, bromo ethane, which is to say that all of these hydrogens here are chemically equivalent. Now, supposing now, as long as you have chemically equivalent hydrogen in the molecule, you will only get one monochloro product. And that is what they are trying to tell us here. Supposing I have this. Supposing I have this. I need your help on this one here. And I do this. Chlorine. Can anybody tell me how many chemically equivalent hydrogen do we have in this molecule? Just give me a number. Okay. How many? Okay, very good. How many? No. This here, this metal here, this hydrogen on this carbon here, and this hydrogen on this carbon here, they are chemically equivalent. So if I replace any one of them with chlorine, I get the same product. On the other hand, if I replace this with chlorine, I get a different product. So therefore, we have two sets of chemically equivalent hydrogen in this molecule. So therefore, you get this product here. That is one product. I will also get this. If I replace the hydrogen in the middle. So in this case, this product, this starting material here, will give me two monochloro products. Two monochloro products. Because you have two sets of chemically equivalent hydrogen. This here, these hydrogens here are chemically equivalent, and this hydrogen here, this here, and this here are chemically equivalent. So now, having given you that information, they said you have a molecule that has a formula C6H12, and when that molecule reacted with chlorine or bromine, you only get one monochloro product. Can anybody therefore tell me what is going to be this compound A? Anybody has an idea what would be the name of compound A? In other words, you must have all of the hydrogen in that compound must be chemically equivalent. Anybody has an idea? Cyclohexane, excellent, excellent, excellent. There are four. The molecule is cyclohexane. Right. That is so correct. Okay. So if you do cyclohexane, react with chlorine in the presence of light, you only get one monochloro product because all of the hydrogen in cyclohexane are chemically equivalent. Okay? And that is the answer to that. So they want you to give the starting material, which is compound A. They also want you to give the product, which is this here, chlorocyclo. hexane. Okay, I think we are just about through to this. Let me do one more or two, and then we'll call it a day, because it's past 9 o'clock already. Okay, no, you guys should be able to do that. Let us go to this. Okay, about this here. Kiara, can you go ahead and read number 18 for us? Okay, maybe Kiara is having problem with mic. Robin, can you go ahead and read number 18 for us?
Draw the structure for 4,2-chlorocyclobutyl 2-methyl lone decay.
On the cane, very good. Okay, very good. Thank you, and very good. So, in this case, they say draw the structure for 4-2-chlorocyclobutyl 2-methyl on the cane. Okay, let me ask you this. What would be the number of carbon in the parent chain of this molecule? Just give me the number. 11. Okay, very good. So it's 11. So let us go ahead and write that. CH3, CH2, 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 that's 4, 5, 6, 7, 8, 9. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay. Now on 2, we have methyl. So I take this out. I place a methyl here. And on 4, we have this complex substituent 2-chlorocyclobutyl. So I remove this. And then what you have, the complex substituent, we have cyclobutyl. So cyclobutane, that would be an alkyl from cyclobutane. Okay. And then you say, if you say this is where the cyclobutane is attached to the chain, therefore this is carbon 1, carbon 2, carbon 3, and carbon 4. So therefore there is a chlorine here, it's a 2-chloro, so therefore it comes to be right here. Okay? Okay, do you follow that? If you follow that, give me a happy face. Okay, very good. Okay. Okay, this should be fairly easy here. Ronald Raymond, can you read 19 for us?
Which of the following molecular formulas is the most likely a cycle?
Okay, thank you. I'm very good. You say, which of the following molecular formulas is most likely a cycloalkane? Any answer to this? You guys should be able to do that. D, that is correct. Okay, very good. We don't need to waste time on that. Just using the formula for cycloalkane, the general formula for cycloalkane, which is HCnH2n. Okay, at C6H12. The N is the number of carbon atoms, as you can see in this case. Okay, let us look at the last question of the day, and then we will call it a day. Okay, Chica Gelling, can you read 20 for us?
Using the formula C4H8O2, write structures for a ketone, aldehyde, carboxylic acid, an ester, a primary alcohol, and an ether. Make sure you identify each structure.
Thank you very much. Very good. Okay, so this is saying using the formula C4H8 and 2 oxygen, write structures for a ketone, aldehyde, carboxylic acid. In other words, we just want to know whether you recognize this class of compounds. Okay, so let us start. Let's start with the ketone. Okay, so we have this here. A ketone, you must have a carbonyl attached to 2 carbon atoms. Okay, so we have that. And then since we only have 4 carbon atoms, so we have this. So at this point, I think we've taken care of 2 of them. This part of the molecule, this is your ketone. It also says give a primary alcohol, and this part of the molecule is your primary alcohol. So we're taking care of those 2. Okay? A primary alcohol is an hydroxy group attached to a primary carbon. And a ketone is a carbonyl, which is this here, attached to 2 carbon atoms. Okay, let us now do an ester. Let's do an ester. Okay, this is an ester right here. An ester is a carbonyl attached to an alkoxy group. Okay, and that carbonyl could also be attached to a carbon or an hydrogen atom. That is an ester. The essential feature of ester, carbonyl attached to alkoxy. In this case, this is an ethoxy. Ethoxy group, okay, attached to carbonyl, and that carbonyl could also be attached to a carbon or hydrogen. In other words, this could also be an ester. Since they gave us 4 carbon to use, keep in mind you must use all of the formula that we have here. Do you want to also draw the electrons on? No, you don't need to show the electrons in this case. The non-bonded electrons, you don't need to show that. Okay, about we've done about ether. And ether, you have oxygen attached to 2 carbon atoms. Okay, in this case we have this. This part of the molecule here, in which you have this oxygen here attached to 2 carbon atoms, that is your ether. They also tell us to draw an aldehyde right here. An aldehyde is this part of the molecule, in which you have a carbonyl attached to an hydrogen atom, and that carbonyl could also be attached to a carbon atom. So this would be an aldehyde. And finally, they tell us to draw a carboxylic acid right here. Carboxylic acid could be this. Keep in mind we have how many carbons? 4 carbons. Okay, for the carboxylic acid, which is this here, you must have what we call a carboxy group. This is your carboxyl group right here, which is a carbonyl bonded to an hydroxy group. And that hydroxy group could be bonded to a carbon atom, would be bonded to a carbon atom, or sometimes an hydrogen atom. And that is your carboxylic acid. Okay, Erin, go ahead and ask your question. Okay, so at this point we have come to the end of today's session, because we are about 20 minutes past 9, and I promised that we were going to be here no later than 9. Somebody said I should give the answer to number 4. Why don't you see me in the office tomorrow? Because anyway, let me give the answer to this. How many valence electrons in this particular instance here? So draw the the structure and semi-condensed structure for this here: 2-chloro, 1-bromo, 2-chloro-cyclobutane. Let us see what that looks like. That is this here. 1-bromo, 2-chloro. Okay, to draw the semi-condensed structure for that, that would be this here. This will be your semi-condensed structure. Now the skeletal structure will be this. Okay, and also now they ask you for the valence electrons. Now for the valence electrons in this molecule, what you need to do, just write down the molecular formula. The molecular formula is C4, because you have 4 carbon atoms here. That's how many hydrogen? 1, 2, 3, 4, 5, 6. 6 hydrogens. And you have bromine, and then you have chlorine. Okay, so once you know the molecular formula, then you put together all of the valence electrons for each atom in the molecule. Here, you know that the carbon has 4 valence electrons. So for carbon, you have 4 valence electrons in carbon. So that is 4 times 4. So that gives you 16. You know that hydrogen only has 1 valence electron, so hydrogen. Okay, so from hydrogen, of course, that is 6. Bromine, valence electron in bromine, because bromine is in group 7, so that is 7. And chlorine is also in group 7, so that means it has 7 valence electrons. So if you add all this together, that is 24, 28, that would be 30. Is that 38? Okay, this is 16, oh no, I'm sorry. This is 22 plus 14, that is 36. 36 valence electrons. Okay, so that is the answer to that. Anyway, folks, we have come to the end of today's session. I hope you enjoyed it, and I will see you in class tomorrow. So until I see you, enjoy the rest of the evening. And I will stay behind for another 5 minutes for those of you who want to ask me additional questions. But those questions will not be online, because at this point I will be turning off the recorder. My office hours tomorrow, I will be in my office tomorrow by 12. I will be in my office tomorrow by